In this video, we're going to derive the equation for the Jeans mass using the Virial theorem. So what is the Jeans mass? The Jeans mass is the critical mass above which a nebula undergoes gravitational collapse. The Virial theorem states that for stable self-gravitating spherical distribution of equal mass, which we can approximate the nebula to be, the gravitational potential energy, so P, is equal and opposite to twice the kinetic energy, 2K. For the kinetic energy, we have the following. This is the kinetic energy in the thermal motion of the gas particles. And N is also, keep in mind that N is also the mass of the nebula divided by the average particle mass. So this can be rewritten as like this. The expression for the potential energy is a bit longer, and we'll explain why it has this form. So we have our nebula. We can assume that it's roughly spherical, and all of the mass enclosed within this area is big M, and it depends on the radius. Here we also assume that the density is the same everywhere, which we could do that. Rho is the density of the nebula, r is the radius, and this is how you obtain the mass. And assume that we have a spherical shell, very thin shell, that we want to raise from 0, so from the center, to some other radius r. So the mass of this shell is small m, and is calculated by multiplying the area of the shell by the density. This is equal to 4 pi r squared rho. Now we have both, and we can plug in. P equals 0 r minus g 4/3 pi r to the third rho 4 pi r to the second rho r dr. And we can simplify this expression a lot. We can take out the constants, so we get 16/3 g pi squared rho squared. So we have assumed that rho is a constant everywhere. 0, r are the limits, and we get r to the 4th dr, because here we've got r to the 5th at the top, r at the bottom, so r to the 4th in the integral. And when you solve this simple integral, you get the following. Yep, big R. And you can simplify this a bit further. 16/15 g pi squared rho squared r to the fifth. So we have this equation, we have both for k and for p, but we need to do something before that. We want for now we want to get rid of this row. So keep in mind that m equals 4/3 pi r to the third row. Put both sides to the second power and solve for rho. So you get rho equals rho squared equals m squared 16/9 pi squared r to the sixth, and this is of course equal to 9m squared 16 pi squared r to the sixth. You can plug this in here, and so for P, for the potential energy, you get minus 16/15 g pi squared at the top, and now you get 9 m squared 16 pi r to the sixth r to the fifth at the top. Now you can simplify this expression a lot. The 16's cancel, the pi squareds cancel, r to the fifth at the top cancels with r to the sixth at the bottom. This becomes 3, this becomes 5, and so after we have simplified, p is equal to minus 3/5 g m squared over r. Now it's time to plug in the Virial theorem, 2k plus p equals 0. So this means that we get 2 times 3/2 m average kVt, and in this case, once we put the p on the other side, we have minus p. Here we also have a minus, so the minus says cancel, and we have 3/5 g m squared r. Over here, the 2 is cancel, the 3 is cancel, and so we also one of the m's cancel, and so we're left with kBt mAv equals gm 5r. Good. So now we want to put both sides to the third power. You will see why in a second. And we want to put this 5 on this side instead to make things a bit simpler. Also, we can go ahead and put the g on this side. Let's do it step by step. 5 kVt times g mAv equals m divided by r. Now put both sides on to the third power as we said. It will make our life easier in a second. Again, keep in mind that m equals 4/3 pi r to the third rho. You can solve for r to the third. This is equal to m 4/3 pi rho. This is 3m 4 pi rho. You substitute this in here. So you have, we can put this on the side. We can just swap sides. 3m 4 pi rho equals 5kBt g m to the third. This m cancels with this m and reduces its power. And so what we have is m to the second power times 4 pi rho divided by 3 equals this term in the brackets here. I'm not going to rewrite it. And now you can put this part of this term on the other side, and so you get m squared equals 3/4 pi rho (5 kBt g m average to the third. And we don't want m to the second power, we want it to the first, so we put both sides to the half power. And we obtain what we wanted. This is the gene's mass, mj, 3/4 pi rho to the power of a half. On this side we have 5kBt g m average 3/2. So this is the expression for the gene's mass. Of course, there are a couple of variations. You can have r instead. You can have the radius of the nebula instead of the density, but you can also write it like this. This is the temperature. So this is the critical mass of the nebula as a function of the density, the average density, the average mass particle, and the temperature. Okay, so this is for this video. I hope I have been helpful. If you have any questions, please write them in the comments, like and subscribe, and thank you very much.